Okay, so let's see how to implement a simple TCP chat with a simple native client. A little disclaimer, I don't have Gundams in the presentation, sorry, and I'm so jealous of your Gundams, but okay, I don't have Gundams, okay. But let's first, I'll present myself. My name is Antonio. I organize this conference. You can find me throughout the internet with that username, Tonio Gela, on GitHub, Twitter, whatever. I run a blog, toniogela.dev. I try to keep a steady pace of posts, but I clearly failed at it. But I wrote mostly about Scala. Another little disclaimer, I will do a little, it's not live coding, but I'll show the result of the presentation. So I've deployed the TCP server and the chat server. So if you go at this URL, you'll find in the releases section of the GitHub page the client that you can download. If you have your laptop there and you want to start in the presentation, I will open the TCP chat client and your messages could appear on screen if you will too. Okay. So the thing that we're going to do today, not directly though, is debunking some myths about Scala. The first myth being that Scala is a JVM-only language. Luckily enough, Daniel already debunked that myth with his presentation. Scala has JavaScript flavor too. But today we're going to talk about, in particular, about Scala Native. Another myth is that there are no libraries or few libraries for Scala.js and Scala Native. And the last myth, for this slide at least, is the fact that native and JS library are more difficult to use. So we won't actively debunk these myths, if not simply using the Typelevel Stack. The Typelevel ecosystem, it's a gigantic ecosystem that comprises of a lot of libraries, and at least the most important libraries, nearly all the libraries, but at least the most important one, were ported for Scala Native and Scala.js. They expose the same APIs. We have really strict policies about that. The API layer has to be the same, and they have almost the same behavior. Of course, there are differences that are due to the platform you're running on, so those cannot be avoided. A couple of other myths that we will debunk during this presentation is the fact that you can do low-level programming in Scala. Scala is sadly often referred to by not so, but by people that doesn't know Scala so much as a JVM-only language that you can use just to develop gigantic distributed system that had to grind data or to instrument Spark, things like that. Is it not the case? Scala is a language with whom you can do low-level programming too, and low-level programming in pure FP style in particular. And to do that, today we are going to be using two libraries of the Typelevel Stack. The first is fs2io. And the second one is scodec. Both are libraries of the Typelevel Stack. Both of them were created by Michael Pilquist, I think. And we will be using it in their JVM flavor and in their native flavor. So what we will be doing today, the meat of the presentation, will be writing a chat server on the JVM using these libraries and writing at the same time a chat client using Scala Native. The nice thing about at least according to me, is the fact that we won't be using REST over HTTP because creating microservices. There are a lot of ways to create microservices using a lot of frameworks. But today we're gonna be creating a custom binary protocol that we will use directly over TCP without relying on all the HTTP layer. We'll do a really low-level stuff. And the nice thing about it is that the server and the client will share this messaging protocol at a build level, literally at a build level. We will use the same code, compiling it to two different platforms. So in order to do this, we have, of course, to set up this SBT build. What we'll be doing is setting up the build using a specific SBT plugin that is called SBT Cross Project that you can import the native flavor using simply SBT Scala Native Cross Project. And as you might see here, the thing that we need to do is simply defining a project called protocol. This project will be a cross project, a JVM and native cross project. It will sit in the protocol folder, so we will use exactly the same source code for both the flavors. And we will be using the dependencies that have fs2.io and fs2 scodec. And as you can see here, and I can probably scroll the slide too, yeah. We will be using the JVM flavor as a dependency for writing the server, and the native flavor as a dependency to write the client. And we will be sharing code in this way. So without further ado, let's see how to implement this specific protocol. Let's see how to write this protocol. As I mentioned before, we will be writing the protocol, a TCP low-level protocol, a binary protocol using scodec. So let's take a few moments to see how the scodec library works. Scodec library, it's a suite of libraries. In fact, again, under the Typelevel ecosystem, it's a library that you can use to manipulate binary data at a really low level. It exposes a bunch of primitives. One is byte vector, that is basically, I will piggyback the isomorphism. It's isomorphic to an array of bytes, but as a concept, but it has better and more handy APIs that work really well with the rest of the library. There is an equivalent representation that is called bit vector. As you can see, you can create it directly passing the 1 and the 0s to a specific string interpolator. And of course, there are a lot of methods that you can use to go back and forth the two data types, from array to byte vector, back and forth, etc. And another thing that obviously scodec exposes, hence the name scodec, it's a codec definition that is really similar to what we are used to for example, while encoding and decoding JSONs. You will use codecs to pass from a case class instance to a JSON representation and back and forth, right? We can do exactly the same thing using scodec to go back and forth from a binary representation to a case class instance. Two other things that scodec gives us that made the library really great are predefined codecs. There are a bunch of them for a lot of different formats, both in little endian and big endian. And they work basically like this. This is the example of a UTF-32 codec for decoding 32 bytes long string. So this is a fixed length codec. And as you can see, using it is as simple as passing the string to the specific codec and calling the dot encode. And but the really funny to use, if you ask me, feature of scodec, it's the fact that it has really a lot of combinator that let you combine this predefined codec in an enormous multitude of ways. And one of this combinator, it's this. It's the colon. It was copied from Shapeless, I think. And in the case the data type you want to serialize is, for example, this case class identity. What you can do is you can define a codec for the corresponding tuple, so a string int tuple, and then, and again, thank you, Nicholas, if there is an isomorphism between, if this tuple is isomorphic to the type you pass to this as operator, so if this tuple, if this is the codec for the binary representation, for the generic representation of this case class, you can use the as operator to go back and forth from the tuple codec to the case class codec. And so basically this codec, it's a codec for our data type identity. And again, as you see, you can pass an instance, get a bit vector back and forth. So from binary representation to an instance of our case class. And that's how scodec works. Now, we will use scodec to write our messaging protocol, right? The message protocol that I decided to use, it's this. I've tried to keep it as short as possible. The idea is that client commands are commands that are meant to be sent from the client to the server, while the server commands, I don't know if that's confusing, I find it clear, and the server commands are the commands that are meant to be sent from the server to the client. In this way, in the client, I can handle server commands, and in the server, I can handle client commands. That was clear for me. Okay, so the thing that we need to do is to then define a codec for these two enumeration, or these ADTs. And funnily enough, the combinators that you have to use in order to write a codec for this are called discriminated. Discriminated, it's an operator that scodec gives you. It takes a type parameter of something that has the structure of an ADT, so a type hierarchy like the enumerations. You can pass a codec that will be used to discriminate between the values. Because you have to imagine that, in particular when trying to decode, we will be getting a blob of byte, and we need to be able to know to which specific client command to deserialize to try to deserialize to. In particular, note that these two commands are isomorphic. And so, to do that, scodec gives you this operator that is called discriminated. You can pass to it the codec for the data type you can use to discriminate between the commands. And you can basically define every type case in this type hierarchy. And so I've decided simply to use 1 and 2 to distinguish between the two commands, and then I pass the codec for that specific command. Again, the generic representation that I casted to the specific type. And so in this way, you can define your codecs. And I will suggest you to use this way. Why? Because you're using explicit discriminators, values, everything is under your control. If you want, you can define even forward compatible codecs and so on. But if you're in the case like me, where you're developing a type project, you might profit from autoderivation. That in Scala 2, it's done via shapeless. In Scala 3, it's done by its generic programming capabilities, and it's supported by the derive keyword, or I don't remember what derive is, reserver keyword, let's say. And so in Scala 3, you can actually simply derive this codec. Scodec will do its magic, will inject a discriminator that I think it will be an integer like I did manually, and it will do its thing. It will give you in the implicit scope both an encoder and a decoder for this type. How are we gonna be? How will we'll be using this codecs? Via FS2's codec. FS2's codec is the library that I added to the build before. It's an interoperability library between FS2 and scodec, and basically, whenever you have a stream of data, the stream, it's a data type that is native of FS2, the other library that we are going to be using. Whenever you have a stream of bytes, you can get a stream of a specific data type using the decoder and using this combinator, stream decoder.many. You pass the decoder for a specific type and you'll get back a function that will take a stream of bytes and get you a stream of that specific data type. In this way, if you have both encoder and decoders, you can use these two functions, these two combinators, to basically hide all the complexity of having to manage bytes under basically a carpet, and you can just care about handling incoming and outgoing data types, instances of case classes. Okay, so now that we've defined codecs, and now that we know how to use them with stream, let's create the data structure, the data type that we will share in the two builds. And I've decided to call it message socket. So what I've done here is I created a trait that will be the only thing apart from the hierarchy of types that I will let the other two projects know, that I will expose to the two other projects. This message socket, it's meant to be a data type that wraps an operating system socket that is represented by this socket IO, that is data type native of FS2 IO. And so we will be sharing this specific trait that exposes a read method that returns a stream of the instances of the specific case classes that we decoded from, and that accept an instance of the case class that we will be sending via the wrapped socket. The implementation is not that important. You don't have to understand it completely, but the idea is that I will take the reads, that is the stream of bytes from the socket, I will make it pass through the decoder, and I will get back a stream of these data types. And at the same time, I will create a queue that it will get fed by this write method, and from that queue I will be originating a stream that will encode to byte those specific instances of case class and send them through a socket. So in this way, if we will be using this message socket data type, we won't have to deal completely with bytes. So the server and the client implementation will have to only to deal with these two parameters that will be typed to, of course, client command and server command. And so the only thing that we will be using in the server and in the client implementation are basically these things. So this type alias, client, and this type server, type alias. And that's basically it for the protocol. So all the code that you've seen so far, it will get compiled at the same time due to the fact that scodec is cross-compiled for both native and JVM. All the code will be compiled to the two flavors of Scala, and all the protocol definition and the way to handle with the data type that are defined in the protocol will be hidden in this protocol package. Implement a TCP chat server using this message socket implementation. So let's create the server. I added memes to the presentation. Okay, so bear with me. The thing that we need to do on a server is, of course, some state. We need some state because the server is the one that is responsible of managing all the connection to it, all the connected clients, so it has some knowledge of whomever is connected, right? And I've decided to store in this state data type that I created all the state that is required for the server to run. And this state, it comprises of a map of string to client. String, it's the username of the connected client. Client, it's the client instance. So the data type that I just shown you, the specific message socket. And basically, I wrote a bunch of quality of life APIs. The most useful of them, it's this broadcast that takes a server command and then that broadcasts it to all the connected clients. And that's it for the state. Then, to implement the server, what are we going to do? As I said before, we will be creating a server that will rely just on TCP without doing anything related to HTTP. So let's see how the creators of FS2IO have decided to deal with sockets using this library. The way they decided to handle sockets, to deal with sockets, it's basically letting the user of their library create a stream of TCP sockets. So the way that you using FS2IO to create a stream of socket, it's this. You call network.io.server and then you bind a specific port. And the idea is that this is a stream of sockets. The idea is that each time someone will try to connect to this server at TCP on that port, each time someone will try to connect a TCP connection to that specific port, a new instance of this socket.io will flow into the stream. And as long as this socket instance will be managed, the connection will be alive. When will finish the handling of this socket, the connection will be dropped by the library itself. So again, as I told before, we will be trying to hide all the complexity related to the fact that we are dealing with a socket sharing binary data and raw bytes. We're trying to hide it under the carpet, and we want to rely on the data type that I created before, message socket, that abstracts over all this thing, right? And so, using an API that it's called evalmap, that it's an API that you can call on specific streams of data, you can pass a function, an effectful function, that will turn your stream into a stream of B if you pass a function from A to IO of B. And what we'll get at the other end of the function call, it's a stream of the return type of this effectful function. So if I decide to pass the constructor of the message socket of the data type that I defined before, what I will get calling this message socket.client on this stream of socket, it's a stream of client. And so this particular structure will function as following. Each time someone will try to connect to this server, to its port 555, each time someone will try to establish a TCP connection, an instance of our data type, client, that it's a message socket, will flow into the stream. The only thing that we need to do now is handle the specific client and use it to communicate back and forth from the server to and the client, right? And so let's write an handle client function. This handle client function has a fancy signature. The signature takes a client specifically and returns a stream. The idea of this function is, while the stream will be alive, the connection with that specific client will be alive. So when this stream will be finished, the connection will be dropped. And so the idea of handling the clients is that we need to run a never-ending stream, perform side effects that are communicating via the specific socket instance, and when we will be done, the stream will finish. The stream will end. So, in order to, using this function, in order to handle at the same time a big number of connected clients, what we'll need to be doing is take those client instances and handle them in parallel. Each handling will return you a stream, and so the main data type will be a stream of streams. And the idea is that each time a client connects, in the upper stream, you'll get an instance of this specific stream that you have to run, and while running it, you'll be handling that specific client. The last thing that you need to do is basically deciding and running them all in parallel. And using this part join operator, you can simply take a stream of stream and decide to run all the internal streams all together and get a data type that is the sum of all the internal streams. So as long as this stream will be running, each connected client will be handled correctly in parallel. The only thing that it's left to do, it's implementing this handle client function, right? And we will need to use the protocol that we just wrote to communicate. Let's see how it can be implemented in a stateless way, using a stateless approach. So the parameter that I'm passing here is, of course, the state. I've shown you the definition of state. The idea is that handling a specific client, you have to have knowledge of the state because you might, for example, want to broadcast a message to everybody else because this is a single room chat client that will broadcast the message to everyone that is connected. And so one of the ways that we can try to implementing it is reading the stream of byte the stream of case classes, the stream of client commands that it's coming from a specific connected client, and handle it one by one using, again, the eval_map function. And again, one of the idea in implementation is handling each of the client's command separately. The reason for whom this is a stateless approach is because you will be able to handle a specific command without any further context. So you can use just the information that are present in the specific command. So one example of the implementation is this. Each time a client will try to request a username to log in, it will try to, we will be registering into the state, and we will send a write command to the specific client to let him know that the registration was successful. Then the thing that we will be doing, just for its quality of life reason, it's broadcasting to every other connected client that it's an information that is present in the state. We're broadcasting the fact that the specific guy connected. Another command that can be handled, it's the users. I won't be speaking about it, but it's really simple to understand. But the problems of this stateless approach will get evident when you will try to handle the specific messages that the client is trying to send to every other connected client. The reason being this send message has no knowledge of who is the sender. We know who is the sender. We should know who is the sender because the sender is this specific client. But in this scope, we don't know its name because it's not evident, because it's not carried by the message. And adding it to the message would let other connected client to impersonate someone else. The only way we want to identify a specific client is via this request username command. We don't want the client to let us to send us the identity for each and for every message that we will be dealing with. So we have a problem here because we can't broadcast this command sending the identity of the sender to all the other connected client to render on the terminal, this guy sent this command. And in the very same way, when this stream will be finalized, will be closing, we will need to unregister it and to tell to every other connected client that this guy is disconnected. The reason we can do that, it's the same. We don't have the name of the guy. So the thing that we need to do in order to handle it correctly, it's the thing that we need to do is to basically handle the whole stream, but in a stateful way. We should wait for the first request username message and then handle the rest of the messages in a similar way, so leveraging this behavior. So let's try to fix that, and let's aim for a stateful approach. Let's rewrite this function. Let's suppose that we already received a request username and we can have the name in this scope. And what we will be doing is simply passing the identity of the guy to the required commands, and we will be use this handle messages function wherever we'll be needing. So I simply isolated the whole handle messages functionality in a further function. So let's see, though, how to use this function, how to use this behavior that I have isolated to statefully wait for the first message. One of the ways to statefully handle streams in FS2, it's using an additional data type that it's called pool. So I haven't spent many words speaking about the stream, but stream, it's basically, as you can imagine, is a data type that it comprises of a series of never-ending IOs or never-ending side effectful function that returns a specific value. So a stream of IO of A, it's a stream of data types of type IO that flows into a stream, and that you can access effectively, just performing side effect at the end of the day, because the data that stays in the stream remains in the stream, very much like the Akka streams library, for example. Pool, it's a equivalent data type, almost equivalent data type, that can be used to represent a stream that completes with a specific value. With complete, I mean that a stream of IO of A, when finishes, it doesn't produce a value. But if you want to produce a value once the stream is ended, you can use the pool representation. The first data type corresponds the second two, so a pool of IO of unit, it's a stream, represents a stream of unit values that flows in the stream. But the last type parameter will be the state that we will get at the end of that specific stream processing. So the way that I've used here to statefully handle this specific stream of incoming data, it's this. I've decided to take the stream of client command that that we are getting through the message socket, projecting this stream to pool, so converted it to the corresponding pool representation, and picking a specific pool representation between the one that this pool method offers us to project to. This Encons one's implementation of pool in particular has this specific really, really long data type. But the idea, bear with me, this is the most complicated thing of all the slides. The idea of this pool data type is that it represents a stream of IO, like the one we have, in which unit values flows into, because we are doing simply side effect, because we are reading and writing from a TCP socket. But this specific pool data type that you get using Encons one, it's a stream that ends with a value that is an option of a tuple of the element that flows in the stream and the possible rest of all the stream of all the possible other values that may flow in that specific stream. And so the idea is that when you have this specific pool instance, the thing that you can do is flat map over it or simply pattern match over it and take a look at what's inside this specific pool. If there's a none in place of this option, it means that this pool hasn't been able to pull anything from the string, and so you're done because the stream ended, and you basically propagate downstream the concept of done, of being done, of the stream having finished. Otherwise, you can try to pattern match on the content. If a sum arrives, it means that the stream that corresponds to this pool representation had some content and something arrived, and we can inspect what arrived. If a client command of type request username arrived, we can use his value to perform operations here, and the other value that we will get, it's the rest of the stream. It's a pointer to the rest of the stream that hasn't been yet pulled. So this is a way basically to do an uncons, the opposite operation of consing, of constructing a recursive list. We are unconsing. We are basically pattern matching over the stream. And the first value that will get us, if the first value that will get extracted, it's a request username, we're basically done, right? Because the thing that we needed was this name parameter in the handle messages function that is the handling that I shown you before. And yeah, the other thing that we need to do is of course register the guy that just connected, send it a message, set username, and alert every other connected client that this specific guy connected. So we will be doing it with pool eval that will let us run IOs, and then we will handle the messages. If you remember, this method returns a stream of unit. So in order to use it inside this recursive call in pool, we have to convert it to pool. And using this .pool.echo, we will be converting this stream that returns handle messages returns to the most simple pool representation. In particular, echo, it's a pool that doesn't end with a specific value, very much like the stream does. So it's technically taking a stream of IO of unit and adding another unit parameter, because this stream, once it will be finished, it won't produce any value. The reason for whom we had to do it recursively is because if you want to handle the case where the first command that was popped out the stream, it's not a request username, we will ignore the value, but we will have to basically recur and re-perform this very same logic. So we will be calling the wait username function using the rest of the stream. So the first command will be popped out, it will be ignored and discarded, and the rest of the stream will be used to reiterate this logic. This whole expression returns this pool representation. You can go back and forth for pool and stream whenever you have to perform stateful or stateless operation, and using simply the .stream operator. And so this handle client function is what we will be wiring in the in our server implementation, and this is all the code that is required to run the whole application. We will be creating the state, we will be creating a stream of sockets that behave in a way I've just explained, and this is the client handling, basically. And of course, the next thing that we have to do is to Dockerize all the application, deploy it, and profit it, but I already did it for you. Now let's see, nearly done, if you're too tired or starving. Now let's see how to implement the client. As I told you before, we will be implementing the client in Scala Native. Scala Native has one big limit, that is that its runtime is single-threaded, but the Cats Effect guys have been able to cram the entire runtime of Cats Effect and put it in a single thread. It uses a lot of trickery and magic that I don't have the time to explain, but it's really awesome. If you ask me after the conference if you want to know about it. Again, we will be creating the client using FS2IO as well, and the implementation of the client, thankfully for us, it's stateless, and it's really easier to write and understand. We will be using the concept of message socket again. This is the entry point of the application. I'm using a library that it's called decline to parse command line argument, but the idea is nearly the same. We will be using this network IO capabilities of FS2IO, not to create a server that was binded only to a port, because the idea is that the IP of the machine will be the IP to which the server will be available to, but we will be pointing at specific IP that should be the IP where you have deployed the server and you have to communicate to that specific port. This network IO of client returns a resource. That's the thing that Daniel cited before, that it's a primitive or case effect that we won't have the time to talk about, sadly. And what you can use once you have been able to bin this specific TCP socket, it's use the socket instance. We will pass the socket instance to the constructor that we created before, to the data type that we created before. It seems seamless, but what we are doing now is leveraging a thing that was compiled to Scala Native, not to simple Scala. And we will be using the instance that we will get simply to connect to the specific socket and handle all the communication with the server. The communication with the server, it's pretty simple to implement. The first thing that we have to do, since we claimed it in our protocol, is sending a request username message in order to allocate a username for us, and that will be the username that we will be using for hold the session. And then we will concurrently, where's the pointer? Concurrently process both the outgoing message and the incoming messages. The incoming messages are pretty simple to handle because we can do it statelessly in this case. So we will be simply dealing with a stream and not with its stateless partner pool. And what we will be doing will be that we will be reading a stream of server commands. And this is the server that will read them, and we will be doing something for each and every case, right? So if once we will receive the set username message, we will be printing a signed username because we reserve that specific username. In case of alert, we will be printing it, and in case of messages, we will be printing the sender too. In the case of the outgoing messages, instead, if we want to give, of course, to the client user the capability to write and send messages to the server, what we will need to do is to repeatedly read the user prompt, right? And each time we will be reading this user prompt, we will be taking the written string and we will be sending it to the server, wrapping it in a send message. And again, the server that is an instance of message socket will take care about everything. It will convert it to the specific byte representation and send it via the socket. And that's this code. It's all you require to write a chat to a TCP chat implementation without relying on HTTP. So now it's time for a demo, if you want to start in it. Okay. I hope that you will be reading. You can connect to it. And there's no one else connected. Come on, guys, help me. I'll ask to Gabriele to connect to the specific. Sorry?
It's on your FS2 chat?
Yeah. Are you connecting, Gabriele? Sorry. Are you connecting, Lorenzo? Sorry. No, it's not trying to, but believe me, it works. So try to connect there. And I'm done. That's my talk. Ask question if you want. Thank you.
I have a question. But so the process outgoing was simply keep listening and waiting for a user prompt?
Yeah, exactly. Okay. Exactly. In the printer implementation that you can see on the repository FS2 chat where you're downloading the client from, thank you, you just sent a quit message. I don't know why that happened, by the way. Okay, clearly that broke, but okay, no, I don't know what's happening. It was working yesterday, of course. Yeah, In the process outgoing process outgoing message, the only thing that I was doing is reading from standard input, but in the printer class implementation, I did some magic with some ANSI code to move the pointer to read and to replace all the text in order to make it behave like chat, in fact. I'm connected, okay. Send message, guys, if it's working, of course, because it was supposedly working. I've tried with 2 laptops at home, so it was working, right? It's working, okay. Gabriele confirmed that it's working. Okay, thank you. You can share, you can show people the fancy feature like shrug. I've added the shrug support. Okay, that's it. /shrug, SHRUG. Yes. There's a structure part. And basically, that's it. Thank you.